Hello everyone. Let's continue the discussion on the microfabrication. In this slide, we'll talk about surface micromachining. Okay, surface micromachining is very unique fabrication method only available on MEMS because you build certain structure on top of the substrate, right? Usually, you do not need such a mechanical structure for silicon fabrication technology. So that's why it's unique for the MEMS. Okay, for example, in this particular cases, like there is a diaphragm here, and then you put the like a serpentine type of the polysilicon piezo resistor here to kind of to get the signal out during the motion of this diaphragm. So this unique structure was built on top of the substrate here at the end, right? There is a polysilicon structure here, and then the additional process can make like a connection using the polysilicon piezo resistor here. So to build this kind of structure, right, you may need a sacrificial layer. Over here, you see the certain empty space, so you need to fill in with certain material, and then you need to remove it. Okay, so so we start to like certain sacrificial layer deposited. Like in this case, is a phosphor silicate glass, and then you pattern it here, and then you make opening to make an anchor for this polysilicon mechanical structure, polysilicon diaphragm here. And then this glass was removed to make like a space that this diaphragm can vibrate. Okay. And then probably additional process you can make this kind of polysilicon piezo resistor to measure the deformation of this diaphragm. So if you take a look into this structure, right? This unique structure built it on top of the substrate, right? We didn't use any etching or anything, right? We just deposit materials, and then eventually you remove the sacrificial layer, and then at the end you have certain structure. So if you have some structure on top of the substrate, you know, like this example, we call this is fabricated by surface micromachining. Okay, so that's kind of the word with particularly pointing out the micromachining means there's this particular process we talk about this is done by micromachining. Okay, so this is you know, many MEMS of structures actually built it on top of this like this structure, right? We try to use the certain structure on top of the substrate like this. Okay, so it says it's the absolute pressure sensor here. This is a micro-machined absolute pressure sensor. Okay. All right. So we talk about the another method, the LPCVD. This is a low pressure CVD. It's a polysilicon. So with this LPCVD, you can build the polysilicon. We're using the LPCVD. But that particular polysilicon is used as resistors, gate electrode interconnection via doping in IC industry. In MEMS, this is used as a central structural material, as I shown you in previous slide, right? So you can use this LPCVD polysilicon as a certain structure. So this particular process that pyrolysis. So to make that LPCVD polysilicon, we thermally decompose the silane at that particular temperature, and the surface side, and then you're gonna build like silicon, and you're gonna build silicon here. So this particular process, you need to control the temperature and then the silent pressure, and then you can control the reaction rate. Phase transition is done by annealing, so you kind of heat up. Using this process, actually, you can transform the amorphous silicon into the polycrystal silicon here. So if you search the material properties of LPCVD polysilicon, it shows the good mechanical properties and then the isotropic properties. Isotropic means its properties is not direction dependent. And then you can control the conductivity and then the also IC comparable. This process is in IC comparable process. Also, it shows the low photo resistivity and then the high thermal process because this is high temperature process, like around 600. So with the what is problem of a high temperature process, right? You should think about the residual stresses, right? In the cases you built on this polysilicon, particularly on top of the certain other materials, because during the temperature down, like you have a different thermal coefficient, some expansion coefficient, and then that cause any during the cool down cause any thermal deformation. Also, it is a stiction problem. We talk about stiction a little bit later. Okay. All right. Silicon nitride and oxide and the PSG. Silicon nitride, you can use the LPCVD. Okay. Also, you can use the PCVD. So this is a plasma enhanced CVD. So you can build both of the process. For the silicon dioxide on our PSG is like a glass material. You can deposit it by LPCVD or PCVD. So you can control basically the question is how about its density comparing the thermally grown silicon dioxide. Okay, problem of this silicon dioxide built through the CVD, its density is less. Okay, what the problem with density of the PSG? Well, sometimes you use this silicon dioxide as like a masking material, and then if you use this silicon dioxide using the deposited by either LPCVD or PCVD, its etch rate, for example, in BOE, right, is greater than the like thermally grown silicon dioxide. Okay. So I have a kind of experience that I put the silicon dioxide as like a masking material. I didn't count this density problem. So I just assume that it is same etch rate, like you want to protect the particular area that by this silicon dioxide. But do not assume this protected area by the silicon dioxide built through the CVD. Right? They are etched quicker than the thermally grown silicon dioxide. Okay, so you need to kind of test whether is it what is their etch rate comparing the material that etch rate that using the BOE. So if you feel the density is not high enough to have a good protection of the those protected area by the PSG, you should think about the thermally grown silicon dioxide. Otherwise, you're gonna get what you want to be. Okay. Also, silicon nitride or polysilicon also can be used as a mask for PSG. If you want to etch the PSG, then the silicon nitride or polysilicon is good for the mask. Okay. Well, let's talk about stiction. But if you Google the stiction, actually, this is not the word actually available, normally available. Stiction is something kind of a new terminology that start used in MEMS. Okay, well, to explain that, let's explain this structure first. Well, if you take a look at this structure, right, there is substrate, and then there is like a space oxide. This is like a sacrificial layer. It will be removed. Okay, and then there is a polysilicon beam. Right, this will be certain like a microstructure for like a sensor actuator. Okay, and then the next step is you want to remove this space oxide to make a room, make a air gap that this polysilicon beam can be deformed, right? Okay, during this removing the sacrificial layer, okay, what problem is the well, probably you know to remove the oxide, right? You have probably use a certain etchant to remove only oxide, and then eventually it will be rinsed by the water. The problem is the you expect, and then you may try to dry out this rinsed water, right? The problem is the when this rinsed water is kind of evaporated by the like oven in the oven, you may expect that this is gone, right? At the same time, but eventually it's not. What happened is the they are kind of from the edge they kind of evaporated, right? And then in the middle, the problem is the well, it's hard to say that, but could be it's evaporate in the middle or at the edge. The problem more they try to evaporate in the middle, but the things the like stiffness, right? Stiffness is lower in the middle, right? If you push in the middle, they the deformation in the middle is more than the deformation at the edge because there is like an anchor at the edge, right? So the problem is you may want this rinsed water evaporated with like a same rate. So it's evaporated at the same time, then you may be okay. But the problem is in the middle. The structure in the middle is softer. The problem is that when they kind of evaporated, then the middle of the structure is kind of when they kind of evaporate in the middle, and then actually, it's not actually released. It's going to touch the substrate because the different stiffness. So it's basically there is a surface tension problem during the evaporation. Okay, so this is called stiction, right? This is this should be released, right? But this structure and software they kind of stick together. So this is called stiction. This is not a wanted situation, right? You wanna have freestanding beam here. Okay, so well that's kind of a mechanism here. There is surface tension that kind of hold your structures to the substrate, and then there is a opposing force because this is like a spring, like anchored from the side. So this is like a spring. So those two forces are balanced. But again, in the middle is like relatively softer comparing to the edge. Okay, so that's why those balance actually this surface tension pull in the structure during the evaporation. Then when the liquid is about to evaporate, this release structure actually touch the substrate. Okay, so this is a big problem, in MEMS fabrication because you want to have a freestanding beam. Okay, so surface tension draw a suspended thin film to surface during the release of the sacrificial. That's the stiction problem. And then large area or low spring constant device that cause the attraction force exceed the restoring force that then make this release structure touch the substrate. Then the question is how do we avoid this stiction problem? Well, the question is you may be, you want to evaporate this liquid very quickly or at the same time. So the things is to avoid the minuscule by the gas phase etching or novel drying method is necessary. minimizing surface energy. So anyway, so we have some special equipment is actually available for this. This is called the um, supercritical evaporator. Supercritical evaporators. Please search the I can write down here, but please search the supercritical evaporator. Then what happens is there is like a map here. There is a status between the liquid and solid, in terms of water, right? The liquid become to gas at like 100 degrees C, and then the liquid becomes solid at like at 0 degree, right? So we cannot avoid this problem when you evaporate the water. So supercritical dry actually, we replace this refill with the instead of water, we use the in supercritical dry, they use the like a solvent. Okay, then they look at the certain path that you can go quickly from the liquid status to the vapor status with certain particular temperature. So it takes not long time, it's just quickly could be done. So that's kind of like a three status location that they those point around that point, three status of the solvent. There is a special point that these three status can exist around that point. So you can have certain temperature and pressure. You can kind of manage it that evaporation path can quickly go through that supercritical point. So that kind of a machine to do that, then this extraction problem can be avoidable. Okay, supercritical dryer is a necessary equipment to do that. Okay, it's not really expensive. This is something is useful to have it in cleaner. Okay, otherwise it's very hard to avoid extraction problem. Okay, well, this is the another method that instead of standard IC fabrication, to build like a certain large area, to improve the productivity. People starting using micro contact printing, like this. You have a certain some material that you want to transport the substrate. Then you kind of stamp, right, with the mold, and you have a certain material deposited on the mold, and then you can have a stamp on top of the substrate. Certainly, the question is how to make sure when this mold contact to the substrate, how can you release this coated material to the substrate? That's the problem. Okay, so that's why the substrate was treated with like a precursor that have a strong kind of adhesion between this precursor to the material that coated on the mold. Then they kind of hold those material rather than this material can move back with the mold. Okay, so that's why kind of having that mechanism. So once this micro contact printing was kind of popular because their productivity is really good, like stamping, right? Okay, so that's another method you can build certain microstructure, micro contact printing. Let me talk about a little bit about the silicon fusion bonding here. Okay, so sometimes we do silicon to silicon, silicon wafer to silicon wafer bonding. Sometimes you have like two different structure was fabricated, and then they kind of put them together. Okay, so so you want to kind of bond between the two. Okay, so this is silicon fusion bonding, as shown here. You have like in room temperature, you have slightly you have silicon dioxide actually deposited here. Okay, and then what you can do is after they put them together, and then you have a high temperature more than like 700 degrees C, 800 degrees C, and then you apply the certain pressure between the two, then this separated silicon dioxide becomes the one layer. Then eventually these two substrate can be like a bonded, like a two bonded like a pit chips, right? So that's what happened here. So this is called the silicon fusion bonding between the two silicon substrate by using the silicon dioxide on top of each substrate. The other method to using the bonding is called anodic bonding. This particular one is good for like silicon and then glass bonding here. So while by placing these two on hot plate, so you kind of heat up, like it's not really high that the previous one, about 300 to 400 degrees C, okay, and then you put them together. Certainly their kind of contact contact area should be very clean. Make sure that they kind of surface have a very good contact between the two surfaces. And then you apply the potential between the electrically conductive hot plate and then the electrode on top of the glass substrate. And then if you apply the high potential here, probably like 700 and then 1200 voltage, okay. And then particularly this glasses like sodium rich glasses, then you can separate their ions, separate their electrode by this potential, and then with this, so you apply the by this, and then you know during this process, actually you can make like a bonding between the two. So it's good, and then you know it's kind of convenient. Okay, so that's good for the glass and the silicon bonding here. All right. Thank you for watching, and then let's move to the lecture 4. All right, see you soon.